All right, let's jump into a seriously powerful tool in calculus, differentials. Ever wonder how a tiny error in one thing can have a huge, almost explosive impact on another? Well, that's what we're here to talk about. Okay, so let's start with a real-world problem. I mean, this kind of thing happens all the time in engineering and science. Picture this. You're building a part for a satellite. Your measurement is off by just a hair, a tiny fraction of a millimeter. The question is, how much does that little mistake mess up your final calculation for, say, its volume or surface area? It could be a really big deal, right? And that is exactly the kind of problem differentials are built to solve. Think of them as this incredible calculus shortcut. They let us estimate the ripple effect of these tiny errors without having to redo the entire calculation from the ground up. It's all about being smart and efficient with our approximations.
Okay, to really wrap our heads around this, we need to get clear on two different ideas. On one side, you've got delta y. That's the actual, honest-to-goodness change along the curve of a function. Then you have dy. That's the differential. And that is our estimated change, the change we'd see if we just kept going straight along the tangent line at that point. And here's a fantastic way to picture it. Imagine you're walking up a curved hill. The actual change in your height, that's delta y. Now imagine that at some point you just decide to keep walking straight ahead on a path that's tangent to the hill. The change in your height along that straight path, that's dy, the differential. And here's the magic. When you take just a tiny step, those two values are incredibly close, almost the same.
So, right, we've got the actual change versus this easy linear guess. Now let's put some math to it and look at the core formula that powers this whole idea. And there it is. Looks simple, right? But this formula is incredibly powerful. It just says our estimated change, dy, is the derivative of the function f prime of x times that little nudge in x, our dx. The truly mind-blowing thing here is that we can actually treat the derivative, dy over dx, as if it's a fraction. We can split it into these two manageable pieces, dy and dx.
Okay, theory is one thing, but let's see this in action. It's time to get our hands dirty with a worked example so we can see how this plays out in the real world.
Okay, so here's the setup. We measure a circle's radius and get exactly 10 centimeters. But, no measurement is perfect. Let's say we know our tool could be off by plus or minus 0.1 centimeters. The big question is, how much could that tiny error in the radius throw off our final calculation for the circle's area? Don't worry, we can knock this out in 3 simple steps. First, grab the formula. Second, find the differential. And third, just plug in the numbers. Let's go. All right, step 1, the formula. We all know this one. The area of a circle is just pi times the radius squared. Simple. Okay, now for the fun part, the calculus. Step 2 is finding the differential. We take the derivative of our area formula. So the derivative of pi r squared is 2 pi r. This gives us our amazing relationship. dA equals 2 pi r times dr. See what that does? It directly connects a little change in the radius, dr, to the resulting little change in the area, dA. And now for the final step, number 3, we just plug in what we know. The radius, r, is 10, and that potential little error in the radius, dr, is 0.1. So what do we get? We run the numbers and bam! The maximum estimated error in our area is about 6.28 square centimeters. And think about what we just did. We figured out how that tiny radius error blows up, all without the pain of recalculating the area with the new radius and then subtracting. So much faster. Pretty cool, right? But believe me, we're just getting started. That was all about measurement error, but this tool is way more versatile. Let's level up and check out a couple more examples. Okay, so differentials can also be used for some quick and dirty mental math, like what's the cube root of 729? I mean, who knows that off the top of their head? Nobody. But we do know the cube root of 8, right? It's 2. That's a nice, clean number. So we can use differentials to estimate how much the value changes when we go from that easy starting point of 8 down to 7.9. So we're going to use the exact same process. Our starting x is 8. The change, dx, is negative 0.1 since we're going down. We find the differential for the cube root function, plug everything in, and boom. The estimated change is a tiny decrease, about 0.0083. So what's our final answer? We take our easy starting value, 2, subtract that tiny change, and we get about 1.9917. And the best part, no calculator needed.
All right, let's try one more, but we're going to add a twist. What if we don't know the exact error, but we know it as a percentage? This is called relative error. So let's say our radius measurement has a possible 2% error. Now the question is, what's the resulting percentage error in the area? So how do we tackle this? Well, we start with the same differential we had before. dA equals 2 pi r dr. But to get to percentages, we're going to do something clever. We'll divide both sides of that equation by the original area formula, A equals pi r squared. Now look what happens. On the left, we have dA over A. That's literally the relative error in the area. And on the right, things simplify beautifully, and we're left with 2 times dr over r, the relative error in the radius. And this leads to a really, really important insight. Look at that relationship. The percentage error in the area is exactly double the percentage error in the radius. So if we started with a 2% error in our radius measurement, that means we end up with a 4% error in our area calculation. This kind of error magnification is a huge deal in so many fields of science and engineering. So let's just take a breath. We've seen how to handle absolute errors, how to approximate tricky function values, and now how to work with percentage errors. It's time to boil it all down to the one big idea that makes all of this magic happen. Here it is, the main takeaway. If you remember one thing, make it this. For any small change, the differential, dy, is a fantastic approximation for the actual change, delta y. We're basically using a simple straight line to guess what's happening on a complicated curve, and as long as our step is tiny, that guess is going to be really, really good. It's an elegant, powerful approximation. So, as you can see, differentials aren't just some abstract thing you learn in a calculus class. They are a genuinely practical tool for understanding how change and error work in the real world. Which leaves me with a question for you to think about. Now that you have this tool, where else could you use it? Think about the volume of a sphere, or maybe financial models, or even population growth. What other real-world calculations could you now approximate?